The purpose of this video is to provide an explanation about problem 4.9 that I had such a difficult time with in class today. And it turns out that the problem is the rounding. In the numerator, as you guys pointed out to me so well, if you use the numbers that actually appear on your paper, you do indeed get a negative number, and there's just no way around it. But if you look at what I have here in front of you, with the 20,299.49, whereas your paper had it as 20,299, which is slightly off, but that wouldn't have caused the problem. The problem would have come in right here. You guys had used, because I had told you to do so, 13 times 530 times 3. And when you do that, that makes that product just large enough to make it bigger than 20,299.49. And so then that makes the numerator turn negative. Because if you do not use the 3 decimal places as I have depicted here, and you just do 13 times 530 times 3, you end up with 20,670, which then is larger than 20,299, and thus you end up with a negative number. So the problem was I had rounded the cells down, and that actually ended up mattering. So I think the rest of it makes sense now. I mean, I think if you just follow along my numbers and put them in, you'll end up with the same thing. Another complexity I encountered when I worked this out to make this video was that if I didn't leave the slope run out to more decimals than we normally use, then I couldn't get the correlation and standard error that Excel would get. So we're just going to leave it like this, even though normally I don't have you do that. But for this problem, just to make it simple, we're going to leave it run out a little longer than we normally would. So basically the slope, just to be clear, for each 1 unit increase in SAT score, we would predict the college GPA to increase by about 0.0034. So if you think about that, that does actually make sense. Now we can go on then over to the intercept. You'll notice I've got here the y bar, which is the average of the GPA, so that's 2.843 minus, and we have the slope multiplied by the average SAT score. Now you'll notice I left the slope a little larger here than usual. I usually have you rounding to 3 decimals. Here is an example where if you round to 3 decimals, you get a pretty different answer. So since there's been so much confusion about this problem, this is what you get if you put the slope into Excel and you calculate it. You get this 1.027. I'm sorry, you get the intercept at 1.027. So we're just going to stick with that for right now. And let's just talk a little bit about interpreting these numbers and then go ahead and graphing them. So for each 1 unit increase in X, which in this case is the SAT score, we expect the GPA to go up by 0.0034. So let's just make a note of that. And for the intercept, we'll calculate it similarly. We can have the y bar, which is the average GPA, 2.843 minus the slope times the average SAT score, which should give us right around 1.027. And the way we interpret that is given an SAT score of 0, we expect the intercept or the average GPA to be about 1.027. So hopefully this clears up the issue from class. I'm going to also show you how to compute the standard error and correlation coefficient using Excel. I'll also put the numbers in the equation for you as well, but I really recommend doing this in Excel. So here's the standard error with all the numbers put in. They're all lined up there, and if you get them all in your calculator in the right order, you end up with 0.498. You can also calculate it using Excel, which I've done over here on the side. Let me just scoot this over so you can see it. The standard error is computed as STEYX, and then I just highlight the two columns that I'm interested in right there, which are B and C, and then I hit return, and I get this 0.4960, etc. So we do need to round that, and we get this 0.496, which is very close to 0.498. So we're happy with that. And then for the correlation coefficient, again, in Excel we'll do that one. So I've computed there the correlation coefficient again, the answer 0.692, and what that means is that it's a pretty strong relationship between X and Y. In order to find out the percent of variation that X explains in Y, we want to take and square our correlation, because this is R, so we want to make it R squared, and when we turn our 0.629 into R squared, we square the value of 0.692 and we get 0.479. And with the coefficient of determination, we can say that in this case, our X, which is our SAT score, predicts about 47.9% of the variation in Y. That's the definition, if you will, of the correlation coefficient. Well, I hope this helps clear up some of the questions about earlier today. And again, I'm really quite sorry.